When you picture the electrical grid, that massive sprawling network powering literally everything around you, you probably imagine, well, just sheer brute physical
Oh,
force.
absolutely. Giant metal towers.
Right, giant metal towers cutting through the landscape, thick steel cables humming with electricity, and like those massive sparking mechanical switches just clunking into place to keep the lights on.
It feels incredibly industrial. I mean, if you drive past a substation today, it really looks like a heavy machinery graveyard.
Yeah, totally.
And for a century, the philosophy of grid management was entirely physical. Like, if an engineer needed to handle more power or, say, stabilize a failing voltage line, they didn't write a line of code.
They just threw more metal at it.
Exactly. They poured concrete, built a heavier piece of metal, and physically jammed it into the circuit.
You threw thousands of pounds of raw material at the problem. But, and this is the core of our deep dive today, the era of brute force is quietly ending.
It really is.
We are moving away from those giant, clunky mechanical switches. The modern grid is shifting toward these sleek, dynamic, converter-based systems. We're talking about technology that essentially creates massive foundational electrical forces out of thin air, virtually.
It's a radical transition, honestly, moving from physical intervention to pure digital manipulation. And to really grasp how we're pulling off this virtual magic trick and the catastrophic traps engineers have to avoid while doing it, we have to look at the underlying physics.
Because the physics hasn't changed.
Right. The rules of electricity haven't changed at all, but the tools we use to exploit them are suddenly completely unrecognizable.
So let's start with the problem itself. Why do we even need to manipulate the grid in the first place? I mean, if a power plant generates electricity, shouldn't it just flow smoothly down the wire straight to your house?
Well, in a perfect frictionless universe, maybe,
Yeah.
but over hundreds of miles of transmission lines, the physical properties of the cables themselves actually degrade the power. You get voltage drops. The system loses its efficiency. And this brings us to a foundational concept in grid management that Sir O'Brien talks about in his lectures, which is called compensation.
Right, compensation.
Engineers have to constantly compensate for that degradation to keep the grid stable.
I always hear that term compensation, but let's break down what is actually degrading. Like, what exactly are we losing over those hundreds of miles?
So to understand that, we need to separate the power in an AC grid into two distinct types. You have active power and reactive power.
Okay, active and reactive.
Active power is the actual usable energy. It's what spins the motor in your blender or lights up your living room.
So that's the good stuff. What is a reactive power then?
Think of pouring a pint of beer.
Always a fan of a beer analogy.
Right. So the liquid at the bottom of the glass is your active power. That's what you're actually there to drink. It does the work. But to pour a good pint, you inevitably get a layer of foam on top. That foam is the reactive power. I mean, you can't drink the foam. It doesn't quench your thirst, but it takes up valuable physical space inside the glass.
Okay, but if it's just taking up space in the wires without doing any actual work, why not just get rid of the foam entirely?
Because without a certain amount of that foam, the liquid goes flat.
Oh, interesting.
Yeah. In an electrical grid, reactive power is what sustains the magnetic and electric fields across the entire system. Without those invisible fields holding everything up, the voltage just simply collapses, and the active power can't travel at all.
You need the foam to deliver the beer.
Exactly. You need the foam.
That makes perfect sense. So if the balance of liquid and foam gets messed up along the journey, the engineers have to step in and fix it.
That is compensation. You basically tweak the electrical characteristics of the line to manage that reactive power. And traditionally, there were two brute force ways to do this.
Right, let's go through that.
The first is series compensation. You take a massive physical component, usually a giant capacitor, and you wire it directly in line, like in series, with the main power line.
So the current has to flow directly through it, kind of like installing a water pump right inside a garden hose.
Exactly. The other method is shunt compensation, or parallel compensation. Instead of wiring the giant capacitor directly into the flow, you build it alongside the main line.
Okay, so more like an overflow reservoir or maybe a water tower sitting next to a main pipeline. It's connected, but it's sitting off to the side, helping to maintain the pressure.
That's a great way to picture it. And historically, pulling off either of these methods required acres of land. I mean, you had literal fields filled with these massive metal capacitors.
Just huge installations.
Huge and Grid operators used massive mechanical switches to basically slam them in and out of the circuit, depending on what the grid needed at any given second.
Which brings us back to the shift we're seeing today. That old mechanical reality is being completely replaced by something called FACTS, which stands for Flexible AC Transmission Systems.
It is a complete paradigm shift.
Right.
We're abandoning those rigid mechanical switches for dynamic, continuous electronic control.
When I first tried to picture FACTS, I initially thought about cars, like moving from a heavy manual stick shift where you're physically jamming gears to a computer-controlled automatic transmission.
Right.
But honestly, even that feels too mechanical. A car transmission still has physical gears meshing together.
Yeah, a better way to visualize the leap to FACTS is to imagine managing a massive raging river.
Okay.
The old mechanical way is building physical dams and giant steel floodgates. If the water gets too high, you winch open a massive steel gate. It's slow, it's heavy, and it takes time.
Right.
Using a FACTS device is like removing the physical dams entirely and replacing them with a localized gravity manipulation field.
Oh, wow. A gravity manipulation field.
Yeah, you're no longer dropping a physical barrier into the water. You are simply altering the fundamental physics in that specific stretch of the river so the water behaves exactly how you want it to, instantly.
That perfectly captures what completely blew my mind in our research, specifically when we look at the absolute star of the FACTS lineup, which is the STATCOM, the static synchronous compensator.
The STATCOM is the ultimate gravity manipulation field in that river analogy.
Yeah.
Its entire purpose is to provide that shunt compensation we talked about, managing the foam, the reactive power, alongside the main transmission line. But it does this without relying on those massive physical fields of capacitors or inductors.
So if you're listening to this and you're picturing giant metal boxes storing electricity, just completely erase that from your mind. The STATCOM doesn't have those massive physical components inside it. It was a converter-based device.
Right. It uses a really simple direct current, or DC, source, essentially just a battery.
Just a battery.
Yeah, but it's paired with incredibly advanced high-speed semiconductor switches. And these switches chop up that flat DC power thousands of times a second, manipulating the pulses to perfectly synthesize an alternating current, or AC wave.
Wait, so it is generating the effects of these massive physical components without actually having them in the box.
Exactly.
It really reminds me of a digital synthesizer perfectly mimicking a massive grand piano. Like if you look inside a traditional grand piano, you see hundreds of heavy physical steel strings and wooden hammers.
Right, massive physical tension.
Exactly. To make a loud, deep sound, you need all that heavy stuff. But a digital synthesizer is just a computer chip and a speaker.
It doesn't have a single string inside it.
Right. But by using an electronic signal to perfectly chop up and shape an audio wave, it pushes the exact same physical sound waves into the room. A concert pianist could play it, and the physical effect on your ears is absolutely identical to the heavy wooden piano.
That's spot on. The STATCOM is literally just a synthesizer for the power grid. It manipulates a DC signal to inject the exact same electrical forces into the power lines, completely virtually.
That is just wild to me.
Yeah, it is. It creates capacitive and inductive effects, managing that reactive power, the foam on the beer, purely through the timing of its software and semiconductors. You're synthesizing foundational physical forces.
Wow.
But, and this is a huge but, this incredible digital abstraction introduces a terrifying new vulnerability.
Because when you remove the giant, heavy physical metal from the system, you completely remove the physical buffer.
Exactly. The physical tolerances of your electrical grid become razor thin.
Yeah.
You're no longer using big, dumb, heavy switches that can, absorb a little sloppy timing.
Yeah, clunky switches, forgiving.
Right. But now you're relying on a delicate, perfectly timed digital signal. And if that software-driven timing miscalculates the physics of the grid by even a fraction of a millisecond,
It'll trigger the hidden trapdoor.
you hit the absolute core danger of modern electrical engineering, which is resonance.
Resonance. This is basically the villain of our story today. I mean, we hear the word used in music and acoustics all the time, but what is resonance actually doing inside a high-voltage power line?
Well, to understand resonance, we have to look at how different components resist the flow of alternating current.
Okay.
In a DC circuit, like a flashlight, resistance is really simple. It's basically just physical friction in the wire. But in an AC circuit, the voltage and current are constantly oscillating, pushing back and forth.
And that back and forth motion creates different kinds of pushback depending on what's flowing through, right?
Exactly. We call that electrical inertia reactance. And there are two main types of forces creating this reactance. Capacitive forces, which store energy in an electric field, and inductive forces, which store energy in a magnetic field.
Okay.
Think of them as pulling the AC current in completely opposite directions. Capacitance pulls the waves one way, and inductance pulls it the exact opposite way.
So they're essentially playing a massive game of tug of war with the alternating current.
Yes. And resonance is the specific dangerous frequency where those two forces, the capacitance and the inductance, become perfectly equal in strength.
The tug of war is tied perfectly in the middle. Nobody's winning.
Right. And because they pull with the exact same strength in opposite directions, they effectively cancel each other out entirely. All of that electrical reactance just vanishes.
Which honestly feels like it should be a good thing, right? No pushback, like pushing a kid on a swing.
Oh, that's a good analogy.
Yeah, like if you just walk up and push a swing at random intervals, you fight its natural momentum. You might even stop it entirely. But if you time your pushes to perfectly match the swing's natural frequency, like pushing right at the peak of the arc, the resistance vanishes.
And the energy magnifies exponentially. With just tiny little taps from your finger, you can get that swing launching higher and higher. On a playground, hitting resonance is incredibly fun.
Right, the kid is having the time of their life.
But on an electrical grid carrying thousands of volts, exponentially magnifying energy with zero resistance is how you melt solid metal.
Oh, wow. Yeah, not so fun.
Not at all. The resistance in an AC circuit, the combination of friction and those pushing and pulling forces, is called impedance. Impedance is essentially the fundamental speed limit of the grid. It's what stops infinite energy from flowing.
So when resonance cancels out the push and pull, that speed limit is suddenly just erased.
It's gone. But how that speed limit breaks down depends entirely on how the circuit was physically wired in the first place.
Okay.
This is where the physics gets incredibly strange. We have to look at the tale of two circuits, really. What happens at resonance in a series circuit versus what happens in a parallel circuit.
Let's start with series. That's the setup where the components are placed directly inside the main flow, the power line, like we talked about earlier.
Right. In a series circuit, when you hit that magical resonant frequency and the forces cancel each other out, the overall impedance of the system drops to zero.
Minimum impedance. The gates just swing completely open.
A total freefall. With zero impedance holding the current back, you get what engineers call voltage magnification. The voltage just spikes to catastrophically high levels, overwhelming the insulation and completely frying the system.
It's just a flood of unchecked power.
Exactly.
So a series circuit at resonance basically turns into a massive, wide-open floodgate. But when we look at the parallel setup, where the components sit alongside the main wire, the physics takes a really wild, almost counterintuitive turn.
Yes. This is the mechanism you really need to wrap your head around. If your circuit is wired in parallel and you hit that exact resonant frequency, the impedance does not drop to zero. It shoots up to absolute maximum. It becomes infinite.
Infinite impedance? Wait, how does a wire suddenly develop infinite resistance? It hasn't physically changed.
It's crazy, I know. But think about what is actually happening between the capacitor and the inductor sitting side by side in parallel. The capacitor is storing energy in an electric field. The inductor is storing it in a magnetic field. At the exact moment of resonance, they stop fighting the main current and start interacting exclusively with each other.
They form their own little private loop.
A perfectly sealed internal loop. The capacitor discharges all of its energy directly into the inductor. And then, a fraction of a millisecond later, the inductor fires all of that energy right back into the capacitor, back and forth, infinitely.
They're basically playing an incredibly fast game of catch with the electrical energy.
Exactly. And they're so perfectly balanced, so entirely consumed by playing catch with each other, that they cannot accept a single drop of new energy from the outside line.
Because their hands are already full.
Yes. To the main transmission line, looking at that parallel circuit, it appears as an impenetrable brick wall. It behaves exactly as if someone walked up with bolt cutters and severed the cable. Engineers call it an open circuit. No current can enter that parallel branch at all, which causes massive current magnification in other parts of the grid as the power desperately tries to find somewhere else to go.
That contrast is just stunning. You hit the exact same physical condition, a perfect balance of forces, but in a series circuit, the gates swing open to zero resistance and a flood of voltage destroys the line.
Right.
But in a parallel circuit, they get locked in an internal loop, creating an infinite brick wall that blocks all current.
And here's the kicker. Engineers are not just sitting in control rooms crossing their fingers, hoping the grid never accidentally drifts into these frequencies.
They're actually using this.
They're actively harnessing these incredibly dangerous forces to build hybrid computer-controlled devices. The most fascinating example of this tightrope walk is the TCSC.
The thyristor-controlled series capacitor.
It is a brilliant piece of engineering, but it deliberately puts both of these dangerous scenarios in the exact same box.
Okay, break that down for us.
As the name suggests, a TCSC uses a large capacitor placed directly in series with the power line to help push power through. But to control exactly how much that series capacitor is working, they wire an inductor in parallel to it.
So we have the main flow going through the series component and a parallel loop sitting right next to it to act as like a control valve.
Yes, and the parallel inductor is gated by thyristors. A thyristor is an incredibly rugged, high-speed semiconductor switch. No moving parts, just solid-state physics.
Right.
The software controls these thyristors, deciding exactly when to pulse current into that parallel inductor. They control this using something called the firing angle.
Which isn't a geometric angle, right? It's an angle of time on the AC wave.
Exactly. It's a measurement of timing down to the microsecond. Think of a combustion engine in a car.
Okay.
The spark plug doesn't just fire constantly. It has to fire at the exact fraction of a second when the piston reaches the top of the cylinder.
Right. If the timing is perfect, the engine purrs.
In a TCSC, the firing angle is that spark. By slightly delaying or advancing the exact microsecond the thyristor lets power into the parallel inductor, the software can smoothly adjust the total compensation being fed to the grid.
It just sounds beautifully elegant. You're surfing the AC wave, adjusting the power flow thousands of times a second without any mechanical clunking.
It is elegant, but the trapdoor is always waiting. Because as those computers adjust that firing angle, constantly seeking the perfect efficiency for the grid, they are dancing right on the edge of parallel resonance.
That game of catch.
Exactly. If the software makes a slight miscalculation, like if that firing angle accidentally pulses the parallel inductor at the exact resonant frequency,
The inductor and the capacitor lock into their internal loop.
instantly. The impedance in that parallel control valve shoots to infinity. It becomes a brick wall. The software tries to pulse power, but the circuit acts like a completely severed wire.
Wow.
The entire delicate balancing act of this multi-million-dollar FastCTS system just collapses in a fraction of a second.
Which really highlights why Sir Abrarali insists on revisiting the basics in his lecture. I mean, you can have the most advanced, artificially intelligent, dynamically adjusting virtual grid in the world. You can have algorithms calculating firing angles millions of times a minute.
Yep.
But if that software ignores the foundational physics of parallel resonance, if it accidentally triggers that infinite internal loop, it basically turns itself into a giant roadblock.
It's the ultimate reality check for modern engineering. We can build endless layers of digital abstraction. We can use statcoms to synthesize virtual electrical forces out of thin air. We can replace hundreds of tons of steel with computer chips.
Right.
But at the bottom of the stack, you cannot program your way out of infinite impedance. The universe still enforces its own speed limits.
It really is like trying to write a line of code to turn off gravity.
Mhm.
You can build a very smart airplane that constantly adjusts to the wind, but gravity never stops pulling. You have to respect the physics or the system crashes.
Which is why understanding the mechanics of these circuits, the zero impedance of series, and the infinite impedance of parallel is honestly more critical now than when we just relied on big, dumb mechanical switches. The smarter the grid gets, the less margin for error we have.
Let's zoom out and just look at the sheer scale of the transition we've explored today. We are watching the electrical grid shed its heavy industrial skin. The era of brute force of mechanical switches and sprawling fields of metal capacitors is fading into history.
It's being entirely replaced by the FCTS era, flexible AC transmission systems.
Right. We are entering a world where devices like the StatCom act like digital synthesizers for the laws of physics. They take a flat battery signal and, through incredibly precise software and high-speed switches, conjure virtual electrical forces, managing the invisible magnetic and electric fields keeping our cities alive.
But as we've seen, that digital precision requires walking a microscopic tightrope. Engineers are constantly navigating the firing angles, adjusting the timing of the grid to squeeze out every drop of efficiency, all while desperately avoiding the hidden trapdoor of parallel resonance.
Because the moment they slip, the components lock into that internal game of catch, the gates slam shut, and you hit the brick wall of infinite impedance.
Exactly.
It is a brilliant, terrifying blend of cutting-edge computer science and deeply traditional, unavoidable physics. And, stepping back from the grid itself, this transition leaves me with a massive question to think about.
Oh, it has implications way beyond electricity.
Absolutely. We are literally watching engineers virtualize the brute force components of the power grid. They are replacing massive steel structures and heavy mechanical systems with software that simply synthesizes the necessary physics on demand.
Yeah, that's exactly what's happening.
So, look around your city. Look at the water treatment plants, the massive physical transit systems, the heavy industrial infrastructure. What other giant mechanical systems are sitting out there right now, taking up massive physical space, just waiting to be rendered completely obsolete?
That's a great question.
Because if we can use a computer chip to digitally synthesize the foundational physics of a high-voltage power grid, well, it feels like the physical world around us is about to become a whole lot lighter.